All right, so hopefully everybody enjoyed your early spring break. An extra 3 days off in the middle of the semester. All right, so I finished chapter 14 on the online video, which was really just more practice problems. There's a little discussion about how concentrations, like Le Chatelier's stuff in there. So I'm going to move on to chapter 15 in order to try my best to make up for the fact that we've lost a lot of lecture days. So we have the individual quiz today. We don't have another mastering due until Monday, so no mastering tonight. And the next science seminar that is coming up is a physics talk, Monday at 3 o'clock in 113, so around the corner. So, any questions about stuff I did on Wednesday? All right, in that case, let's move on and do some acids and bases. So,
Can I ask a quick
sure.
question? About coefficients when you're dealing with ice tables
Mm-hmm.
and stuff. So if do you carry the coefficients down into the change?
Mm-hmm, you do. Yep.
It carries down. Okay.
Yep, the coefficient carries down. All right, let's then apply all of that stuff about K's to systems. So just as a refresher, we have some definitions of acids and bases. And there's two different categories that we can put our acids and bases into. This is the more common one, probably the one you're familiar with, the Arrhenius definition of acids and bases. In the Arrhenius definition, an acid is any molecule or compound that releases a proton in solution. Just as a reminder, H plus is a proton, which is a hydrogen that lost an electron. Right, hydrogen only comes with one electron, so when it loses the electron, it becomes H plus. If it loses the electron, the only thing left in it is a proton, which is where it gets its name from. So it's a proton, single proton hanging out. So an acid is something that releases a proton in water, and a base is going to be something that releases, does anyone know what an OH minus more commonly called? Yep. A hydroxide. So, this is probably how you've seen them written, right? I have hydrochloric acid. The AQ means it's in solution. Is HCl, by the name it's an acid, is it an ionic or a molecular compound? Right, ionic. So it's going to break into its two ionic parts. And so it started off as an acid, and now it's released a proton. So by definition, that's an acid. Right? Because one of my products is a proton. All right, we could also take a look at this guy. All right, sodium hydroxide. Again, is this guy ionic or molecular? Ionic, right? So we're going to break into our 2 ions. And so one of my products now is the hydroxide, which means using the Arrhenius definition, that is now a base. Okay, that's probably the definition you're more familiar with. The one we're going to use, though, is the Bronsted-Lowry definition, which is similar. But it makes determining the balanced chemical reaction much easier. So it sounds funny now, but when we start to use it, you'll find this is the better choice to use. So an acid is any substance, molecule, compound that donates a proton, which means a proton will be one of the products. And a base is going to be a substance that accepts the proton. So it's a matched pair, right? One's giving up a proton, the other one's taking the proton. So if we look at a balanced chemical equation, I'm going to take the same hydrochloric acid, but now I'm going to explicitly write the fact that it's interacting with water. All right, so hydrochloric acid, based on our definition, will donate a proton. Who is going to be the acceptor of the proton? Water, right? If this is donating, this must be the receiver. And we will write water like that. Right, so water's accepted the protons. Now it's H3O plus. And that leaves us with our chlorine. All right, bunch of different things going on here in this equation. So we know that this is our acid, right? What then is the water acting like in this reaction? It's a base, right? Because it's going to accept, so we're going to call that the base. Now we've just spent a bunch of time talking about equilibrium. So this reaction could go in reverse. We'll talk about later why that's not likely in this particular case. But it could go in reverse. So if I was going to look at these two sides as a possible reactants, is this compound, this H3O plus, going to donate a proton or accept another one? It's going to donate. So if it's going to donate, it's now the base. And this must now be the acid. Oh, what did I just write? Oh, you're right. There we go. So when we use our Bronsted-Lowry definitions, there's going to be an acid and a base on the reactant side and an acid and base on the product side, and they're going to be opposites. Paul?
So just out of curiosity, besides the fact that we know that HCl is an acid, if we didn't, however, you could look at H2O and HCl and kind of say either or could donate hydrogen. So how do you determine which is acid or base, not knowing what the substance is, I guess?
You will either look at the table of acids and figure out which one of your two reactants is an acid, or based on the name, I'll try to be very specific, like we're going to use phosphoric acid. Try to get some very specific hints. Because you're right, water can act as both an acid and a base, and it could be confusing. But the examples we're going to be using are going to be pretty straightforward. So, because we're just learning, just stretching our acid-base muscles. See, that's funny, lactic acid muscles. My workouts were all canceled for Tuesday, Wednesday, Thursday, so I went and worked out today. She made it extra super hard because we had missed 3 days. So my arms are a little burny. All right, so if we have all that, oh, let's see, where was it? Okay, no, we're good. All right, so we could do a similar thing for this reaction. All right, so now I have ammonia and water, making ammonium and hydroxide. So looking at just the left-hand side of this equation, is the NH3 or the water going to be the proton donor? The water is going to be the donor, right? Because the NH3 goes from NH3 to NH4 plus, so it's gained a proton. So if this is the donor, then this is the acid, which means this must be the base. So if water is the acid on this side, it's the base on this side, and it's the acid on this side. Right, so there's going to be one of each on both sides of the arrow, and they're going to reverse roles. So the water was the acid, then it's the base. The NH3 was the base, so it's the acid, one on each side. So I think these definitions are easier because there's like two ways to check to make sure you've labeled them correctly. You should have one of each, and they should reverse roles on either side of the arrow. All right, so we have hydroxides, we have protons. The only thing we haven't named is this guy right here. And H3O plus is going to show up a lot in these next few problems. And this is a hydronium ion. So we're going to talk about protons, hydroxides, and hydroniums, because all the reactions we're going to talk about occur in water. So we're going to see a lot of this H3O plus species. All right, how do we feel about that? Good so far? Okay. Let's then look at how these acids can operate in solution. We're going to fall into two big categories, which you probably are familiar with, right? Monoprotic and polyprotic, or anything more than diprotic, triprotic. So by definition, right, we have mono, which means one. Protic comes from the word proton. Right, so monoprotic tells you one proton. So if I have an acid, I only have one proton to donate. If I have a base, I can only accept one proton. So things that are acids that are monoprotic are like the ones we just looked at, hydrochloric acid, nitric acid, and my go-to favorite, we use this guy a lot, acetic acid, right? My strongs and my weaks. Some of my favorite monoprotic bases, hydroxide, ammonia, so those will all be species that can accept only one proton. All right, so then if I have polyprotic, using the same method, right, many protons. These are acids and bases that can accept or donate more than one proton. So for acids, it could be something like sulfuric acid. So looking at that, how many protons can sulfuric acid most likely donate? Right? 2. It can do 2. What about my other favorite, phosphoric acid? How many protons could it possibly donate? 3. Okay. So then we could have the sulfate ion as a base. And how many protons does it need to get back to neutral? 2, which should make sense because these two are related. We could also do this, right? The phosphate ion. And they would need 3 to get back to neutral. And that's going to come into play when we start looking at balancing these chemical reactions using these acids. Either it's going to donate 1 or it's going to donate more than 1, and we'll have to figure out how to balance them to make it even. Good there? Fairly confident on definitions? Okay. Let's look at how they pair up. All right, so a conjugate acid-base pair is a pair of compounds that differ by the presence of a proton. Every reaction between a Bronsted acid and Bronsted base has two conjugate acid-base pairs. So pretty much what we just did, but now we're going to define it. So let's say I have this reaction. All right, so I have this hydrocyanic acid and water. So if this is an acid, by the fact I'm calling it an acid, is it going to donate a proton or receive another proton? It has to donate. Who is going to accept the proton? So what will one of the possible products be made? Right, H3O plus. Okay, so if that's true, what must be the other possible product? Right, the only thing that's left are CN minus. All right, and so since I already called this an acid, I know for sure that's acid. So then how is water acting on the left side of my reaction? All right, acting like a base. All right, so if this is an acid, that's a base. What is the hydronium ion acting as? It is the acid. So then what is the cyanide ion? Acting like a base. All right. If that's all true, what is the conjugate pair of my hydrocyanic acid? The CN minus. So this guy and that guy are conjugates of each other. It was an acid, now it's a base. Because, right, they're opposite, differing only by a proton. A pair of compounds that differ by one proton. This guy and that guy differ by one proton. All right, so then that means that these two are also conjugates. Which this is a reaction between an acid and a base and has two conjugate acid-base pairs. All true, right? It's an acid-base reaction, so I have two different conjugate acid-base pairs in my reaction. All right, so let's do it again and try a different set, see if we can label all of these items again. All right, so let's take a look at this acid-base reaction. All right, looking at the overall reaction, can my CO3 2- donate any more protons? No, right? It doesn't have any protons, so it's going to accept protons. So if it's the acceptor of the protons, is it acting like the acid or the base? It is the base in this case. So if I have a base on the left, what must water be acting like? It is an acid. Good so far? Okay. So that's all true. Then, we have hydroxide over here. Is hydroxide going to donate another proton, become O2-, or is it going to gain a proton and become water? It's going to want to gain one. Don't ever lose a proton off of hydroxide, become free-floating oxygen elemental. Bad chemistry, bad chemistry. Okay, so if that is going to gain one, then it must be the base, and this must be the acid. All right, so then let's pick our conjugates. Who is the conjugate of water? Right, this guy. So then, by default, these two must be conjugates. Okay, so for some of the homework coming up, not till actually next Wednesday, you're going to be able to pick out the acid and the base on each side, Who are the conjugates? Let me ask this as a follow-up question. What is the overall charge of the reactants? These two compounds, what's the overall charge between the two of them? What should be the overall charge on the product side? -2. Do we get to -2? That's going to be the other key thing you want to keep track of. Overall charge. Whatever you start off with on this side, you must have the same charge over here. So that may help you predict what some of the products are. If you know for sure one of the things is hydroxide, not exactly sure what the other one should be, the charges have to even up. So besides being mass balanced, that we have the same number of carbons, hydrogens, oxygens, you also have to have charge balance, left to right. So when we start predicting these. Feeling confident? I'll take silence as a yes. Good. Last thing on this slide before I get too far away. What's the crazy thing about water between the first equation and the second equation? Right? The first time I use it as a base, and the second time I use it as an acid. There's going to be a bunch of molecules that have that capability, and we call them amphiphilic. Amphiphilic just means ability to act as an acid or a base. So water right now is in the middle. It could either lose a proton, become OH minus, or it could gain a proton, become H3O plus. It's okay with that. But like things like this, hydrocyanic acid, can only lose. Like there's no way for it to gain another proton. That's not possible. What about this guy right here, this HCO3 minus? Can it lose a proton? Does it have the ability to gain another proton? Yes. So this would be another amphiphilic molecule. Right now, if I'm using it as is, I could start a reaction and potentially lose a proton or gain a proton. So we're going to run into a bunch of molecules that have that capability. Good. Good, good, good. All right. Well, let's get ready to do some calculations. Now we got our definitions down. We're feeling good about what is an acid, what is a base. So the reason this chapter comes after the one we just did about equilibrium is that we're going to use those big K's to predict equilibrium concentrations of acid-base reactions. Yay! All right. So in every aqueous solution, we have the following reaction. So water has the ability to interact with another water and do an acid-base reaction, right? Transfer protons from one water to the other water. Water is constantly doing that. These are called auto-ionization reactions because it means that they are spontaneously becoming ions and then reversing, going back to neutral. So auto-ionization. Which, as you can see, is also an acid-base reaction, right? We have one water donating a proton, the other water gaining a proton. Which means now we have a snazzy reaction that we can make an ice chart from. So let's go ahead and do an ice chart. I know, ice charts are my favorite. Super favorite this. I just love them. You just wait. Later in this chapter, we're going to take ice charts to the next level and do them in moles and figure out how to make pH titration curves. I know, tantalizing, very exciting. Just wait. All right, so I'm going to rewrite this equation so I can make my ice chart. going to say our textbook is great about explaining ice charts, so if they are a little perplexing, our textbook does a really, really great job of walking you through how to set up the equation, how to set up the tables, what to put where, and then how to solve them. So if besides coming to class or my office hours isn't enough, I would highly recommend going through the example problems in the book. Oh, okay. Postpone. The funny thing is, like, even if I restart it to update it, everyone else who's an authorized user also has to update. It's very confusing. So it gives me this issue every single time, because even though I've restarted, the other 18 professors haven't restarted. Computers. All right, so here we have our fancy ice chart. What do we know about liquids, pure liquids in an ice chart? They don't count. Pure liquids and pure solids do not count. So I'm just going to write a little dash through those lines so that they're included in the table, but they don't count towards equilibrium. So imagining that I started off with pure water initially and 0 of those two components. Bless you. I would, right, gain some amount x, which then makes my equilibrium right there. So if I were to write out my K for this particular reaction, do the products of the reactants go in the numerator? The products go in the numerator. Do I need to raise them to any powers? No, right? Because they're 1. What do I put in the denominator? I can't put nothing. If I put nothing, that's the same as 0. So I got to put something. 1. Which is not nothing, it's 1. Yeah.
It's the same thing as saying H3O plus multiplied by OH negative.
It is. It's over 1. True. I'm just being more specific. All right, and then we solve that, so I know now it's x squared. Right? X squared. So, using the experimentally determined equilibrium constant, for K, you can keep writing down, I just ran out of space. So experimentally, the equilibrium constant for water is 1 times 10 to the negative 14th at 25 degrees Celsius. How do I get the x by itself? Square root. All right, 1 times 10 to the negative 7th, which I just said, right, based on these x's, that they are equal. Right, so the concentrations are equal and both equal to 1 times 10 to the negative 7th molar, which should seem like an important number when we're getting towards pH, right? So when I'm thinking about pH scales, if I have a pH of 7, what does that tell me about my solution? Neutral. Right? It has no charge, there's no dominance protons, hydroxides. You just mathematically proved that. Yay! You guys don't seem nearly as excited as you should be. You had a piece of knowledge last semester that now you can mathematically prove is true this semester. That's pretty cool, right? Okay. So, let's talk about, I didn't leave myself any space. Okay. If you have an acidic solution, which one is in dominance? The hydroxides or the hydroniums? Hydroniums are in dominance, okay? So if that is true, it means that the hydroniums have a greater concentration than 1 times 10 to the negative 7th, and the OH minuses must have a lesser concentration. If I have a greater value than 1 times 10 to the negative 7th, it would be something like 1 times 10 to the negative 6th, or to the negative 5th, or negative 4th, which, as you know anything about the pH scale, right, The smaller the number, the more acidic. So that's where they get that from. If I have a base, the opposite is true, right? Which means that these hydroxides will have a greater concentration than hydroniums. But it's really, really complicated to think about things in terms of, right, this actually means 0.0000001. It's hard to compare things on that small of a scale. So we don't often refer to these acids and bases concentrations because the amounts are really tiny. So what we're going to do, we're going to turn them into the pH scale. So the pH scale is a way of describing, more appropriately, the hydronium concentration in the solution. It's a way of measuring acidity. So, pH is defined as the negative log of the hydronium concentration, which makes sense when you think about what I'm trying to say here. This little p in math means take the negative log of the thing that's next to it. So it's more really appropriate to write as pH plus, which would be take the negative log of the hydroxide, or the hydronium concentration. But that's wordy, so we just call it pH. All right, and then I could do the reverse if I just wanted the concentration by itself. I would use the power of 10 and raise it to the negative pH. Okay, so for the neutral solution, we just solve for on the other side, where this, right, that was true. If I wanted to figure out the pH of that, which, if you have your calculator out, you can go ahead and plug it in and prove it to yourself. Negative log of 1 times 10 to the negative 7th. Is 7. All right, so that's good. That answers half of the questions we have about solution. Then we also have to think about, we don't use this very often as a scale, but it's super useful to know how to do. The pOH. All right, so the pH scale is what everyone uses to figure out how much stuff they should add to their swimming pool. But in chemistry, it's just as important to be able to do the pOH, because we want to be able to look at both sides of our reaction. So best guess, I'm going to take the negative log of the OH in order to figure that out. All right, so then the same would be true if I wanted to figure out just the hydroxide concentration by itself. All right, so I have 2 practice problems, and then I'll stop, see if time to do your quiz. So let's say I know the pH of my solution is 1, but I want to figure out the concentration of hydroniums and hydroxides in the solution. All right, so we can definitely do, right, or rewriting it the more useful way. plugging in the pH that was given to us. .1 molar. All right. So then the flip side of this question is, how do I go about figuring out the OH concentration? Well, if Kw is this, I could say this. Right, so if I took the negative log of everybody, negative log of KW is that, negative log of that numerical value. Take the negative log of these two things, which we just said previous slide is pH and POH. And if they were multiplied, but now I'm doing the negative log, they'll be added. Right, those crazy rules about logs. Look at that, pH plus POH equals 14, which is what you already knew about acid-base chemistry, right? The scale is 0 to 14. This is why. Because at neutral pH, all hydroxides and hydroniums have a constant molarity of 1 times 10 to the 14th, which is where that scale number comes from, which means they're even. So if I know the pH is 1, back to the problem. If the pH is 1, what must be the POH? 13. Which means I can now figure out the concentration of hydroxides. Look at that. I just proved all the stuff you already knew using math. Yay, math. Yeah, you guys can cheerleader. Yay, math. All right, I will do this other problem Monday. I want to make sure you guys have enough time to get yourself ready for the quiz.